Welcome back to Physics Clinic at the Red Rose Academy. Today's topic is we'll see how the torque is exerted. Okay, so we are going to study about the torque in a uniform magnetic field. Actually, the torque you have learned that is in a uniform electric field also. So right now you are going to learn about the torque in a magnetic field. So I'll explain you in detail right now. Already we saw so many uh, topics based on this force, how the force is exerted. Okay, so the major difference between the electric force and the magnetic force, everything we have learned, right? Magnetic force is Q times V cross B. There is velocity over there. So here, how it can be explained. So everything we'll see now. Okay. So here we have considered a rectangular coil. So a rectangular coil is placed in a uniform magnetic field. Okay. So here you can able to see this. A rectangular coil in a uniform magnetic field. So now the magnetic field is between the two horseshoe magnet, both north and south pole of a magnet is here. And then here what is the resultant from the north pole to south pole, there is an uniform magnetic field. Now this coil is there. So in the rectangular coil, a wire is wounded. Okay. So n number of turns of wire is wounded so that it can be connected to a battery. Okay. So current is passed through this particular wire. And then through the passage of current, there must be the magnetic field around it. And also this magnetic field causes force also in it. So how the forces will be? So based on the coil. So here the current is flowing like this. So if the force here acting downwards in the left side, I'm saying. So here, if the force acting downwards, right side, here the current flows from C to D. So initially the current is flowing from A to B. Now the current is flowing from C to D. How the force will be? The force will be upwards like this. Okay, so there are two forces acting on it, so that we call this as torque, a couple of force, okay, which causes the twisting. Okay, so here, so what is happening if you consider this as a rectangular coil? Okay, like this rectangular coil is available. So and then right now you are wounding the wire in it. So through the wire, the current is passed through it. So through the wire means this wire is connected with the external power supply. So current is passed from this to this. Okay, from A to B and B to C, C to D, like that. So A to B, the force will be, so due to this current, due to this passage of current, if the current is like this, if this is the straight conductor, then the curl of the finger represents the magnetic field direction. So the magnetic field direction will be like this. Okay, so that the force acting, F cross B. So the force is acting downwards. So the force is pulling downwards, this one. And then due to the current, see here, so A to B, B to C, C to D. C to D, the current is passing. So it is in the opposite direction of A to B. So that the current is, now if you are checking with this here, okay, the magnetic field is moving in and out like this. Okay, if you keep the finger like this here, the magnetic field is moving in and out like this. So here what will happen? The magnetic, due to this magnetic field, the force acting upwards. Okay, one force is acting upwards, another force is acting downwards, so that it can rotate. Okay, so that there is this rectangular coil, right now it is along with the magnetic field direction. uniform magnetic field direction, which is external magnetic field direction. Right now, what is happening? Now, due to this particular motion, so a torque is exerted here. A twisting force is exerted here. A couple of force acts on this particular rectangular coil. So what will happen due to this? The coil turns, the rectangular coil turns. So there is a force experienced by this particular coil. So we'll study about the AC circuit later. So in AC circuit, this is the principle behind that. So whenever there is a current carrying coil, there must be the induced magnetic field. Due to that, the forces are developed across, okay, the rectangular coil, or we can say torque is exerted over the coil. So that twisting force causes the coil to rotate. Okay. See, for example, you are constructing here in this might be A and this might be B. The length here, the length is given as B and the breadth is given as A. Okay, if this is A, this is also A, this side is B. Okay, you know that. If total is A, then if you take the midpoint, then the midpoint will be, until the midpoint, it is A by 2, A by 2. So the force F1 and F2 we can consider here. So what is the force F1? F1 is I into B. So the length of this AB is B only, right? So there is current I pass through that. So I into B into capital B. Capital B is the magnetic field. Okay. Then what is F2? F2 will be I into B into capital B. So that is also here, right? So only the direction changes. So the force will be F2 also equal to F1. Okay, equal and opposite it will be like that. Okay, so the net force on the loop is 0. If you consider the loop, the net force on this particular loop is 0. So there is a torque on the loop, everything I've discussed. What is the torque? It tends to rotate in anti-clockwise. So like that we saw here, right? One force acting downwards, another force acting upwards. So it is in the anti-clockwise direction. The coil is moving in the anti-clockwise direction. Okay. Then you know this torque. What is the magnitude of the torque? You have to add both the forces. Okay. So what is the force? F1 times A by 2 plus F2 times A by 2. You know torque is equal to R cross F. Okay. So what is R here? R is the distance or displacement we can take in here. So A by 2 into F. F1 and F2 we can take. Then F1 you can substitute this value. F2 you can substitute this value. Then it will be 2 times half plus half will be 1 time. I into B into B and AB is here. A by 2, A by 2. So it will be 1. So I, AB into B will be here. So what is A and B? A and B are the length and breadth of the rectangular coil. So we can write the area of the rectangular coil. So instead of writing the length and breadth A and B, so you can write the area of the coil and B. Okay. What is the area of the coil? AB is the area of the coil. Can you able to understand? Can you able to imagine this? Okay. So we next consider the case when the plane of the loop is not along the magnetic field. We can consider this case, but makes an angle with it. We take the angle between the field and the normal to the coil be theta. Okay, so we can consider all the cases, the theta, some angle. Okay, the theta might be, so now the triangle, rectangular coil will be like this. By means of this particular force, it moves in a anti-clockwise direction and it forms, actually it is the twisting force, the angle theta will be 90 degree if it completely moves. Okay, like that it shows everything. And you know about this. And I told you what is that. So here, no, so many things are not explained clearly. I told you, no, F1 cross A by 2. R cross F. Okay, that is tau. Keep this in your mind. So, and plus F2 cross A by 2. So, sine theta and sine theta will come. Okay. Both create same angle. So, twisting happens at the middle. Suppose if it twist particular distance like this. So, the twist is happen at the middle. Okay. Then both side it forms an angle theta. Like this, it's shown in your figure. See? see, it creates an angle theta, right? Like this it is. Okay, both the side, you can say it is theta. Can you able to understand this? Okay, so a by 2 sine theta plus a by 2 sine theta it will be. Then IAB sine theta from the geometric side also you can able to take. Okay, see, for example, this is a by 2, this is a by 2. From this position, it now turns, twist like this and forms an angle theta. Then if you construct a right angle triangle, okay, what is this particular thing? Okay, if this is theta, this will be theta. So it is 90 degrees. So a by 2 is the hypotenuse side. This particular side is the opposite side. So opposite and hypotenuse can be connected by sine theta. So sine theta is equal to a by 2. I mean, opposite by a by 2. So a by 2 sine theta is the opposite side. Can you able to understand this? Likewise, you can construct a picture here. That is also a by 2 sine theta. Okay. So it shows. So here also this AB, don't confuse with this A and B and then this AB. The small AB is the area of a rectangular coil. Okay, you can write in your notebook. Otherwise, you might get confused. Okay, so area of a rectangular coil, AB. So A is this particular area. You can replace AB as area of a rectangular coil. And this B is the magnetic field. B is the magnetic field and sine theta. Okay. Then you can apply the cases when theta will be 0, the forces of the couple also approaches to 0, the perpendicular distance between the forces. Okay. So you know all these stuffs. It's very simple only. This makes the forces collinear and the net force and torque will be 0. Okay. So then it can be expressed as vector product of the magnetic moment of the coil and the magnetic field. We define the magnetic moment of the current loop as, what is the magnetic moment of the current loop? Always you represent this as P suffix M. That also you can represent, or M also you can represent. This is a vector quantity. M vector is equal to I into A vector, like that. Okay. So, what is the what is the electric dipole moment? Electric dipole moment is Q into 2A, right? Here, instead of Q, you need to take I. Okay, instead of the length, you have to take the area because area wise only we are seeing. Okay, so and then tau is equal to M cross B. Instead of taking that force and this particular IAB sine theta, right? In this you can take what is I into A into sine theta? So you can take IA as M. Can you take like this? Tau is equal to IA can be replaced by M or P suffix M. P suffix M is nothing but it is the magnetic moment. Okay. So M into B sine theta. Okay. So that means this M also perpendicular vector. So this is also a vector. So you can represent this as a cross product. So M cross B. Because sine theta is there, no, it is a cross product. Can you able to understand? See, that's what. This is the magnetic moment. This M is magnetic moment, P suffix M. You can represent like that, then it won't be confusing for you. Then P suffix E is the dipole, electric dipole moment. Okay, so it is the torque due to the electric field, it is the torque due to the magnetic field. I hope it is clear for you now. And if there are n number of rotations, you have to replace. Okay, you have to add, you have to multiply with the n also. Okay, when we saw already. Okay, suppose a state of equilibrium. Okay, what is the state of equilibrium? No torque on the coil. That is the state of equilibrium. Okay, when what is the torque we saw? M cross B, or we can say magnetic moment and the magnetic field. If magnetic moment and the magnetic field are parallel like this, then what will happen? Sine theta will be 0. Okay, the equilibrium is a stable one. Is it clear for you? Any small rotation of the coil produces a torque, means which bring it back to its original position. So that is the meaning here. Okay, if this is the coil, if it rotates a very slight angle, then it come back to its original position by means of attaining its equilibrium position. Okay, then when suppose if you consider when they are anti-parallel. Okay. Then what happens? The equilibrium is unstable. Correct. So if M and B are anti-parallel, parallel means 0 degree. So anti-parallel means 180 degree, like that. In that it is unstable, as any rotation produces a torque which increases the amount of rotation. That means it tends to increase the amount of rotation. That's what they are trying to say. Okay, the presence of a torque which increases with the amount of rotation. That's what they are trying to say. Okay, so then this presence of torque is also the reason why a small magnet or any magnetic dipole aligns. That is the main reason with the external magnetic field. Here you must understand, due to the current flowing through this coil, okay, A, B, B, C, C, D, D, A. Like that also you can consider whatever it might be. So due to this current passing through this particular coil, okay, there is a magnetic field. That is the induced magnetic field. There is a magnetic field outside also, external magnetic field by the horseshoe magnet which is placed. Okay, so the rectangular coil is placed in between the horseshoe magnet of north and south pole. So it is under the what actually it is under the equilibrium condition, or we can say what is the equilibrium right now. So M and B, what is M? Magnetic dipole moment, magnetic moment. And what is B now? Magnetic field. So both magnetic moment and the magnetic field are parallel. Okay, then it will be, actually it is in equilibrium, but it can slightly increase, we can say it can slightly twist it, try to slightly twist, but it won't. There is no torque on the coil. Okay, there is no force acting on it because these two are parallel. No, if these two are anti-parallel, M and B are anti-parallel, then what will happen? It has slight increase in torque. That's what they are trying to say. Okay, so that due to that the equilibrium is unstable. It won't exactly attain equilibrium. The equilibrium is unstable due to this torque. Clear? Okay, if the loop has n closely wound turns, then you know all these things. So this presence of the torque only the reason why a small magnet or any dipole aligns itself with the external magnetic field. So this is a very important point you must underline in your book. Okay, and take a note of it and go through this example. This example is direct only. You're applying the formula. So try to keep every formula in your mind. Along with your unit, you have to derive its unit. Okay, don't mug up the unit. Students, I taught you so many times how to derive the unit. Okay, clear? There. Okay, go through this. Then we'll see circular current loop as a magnetic dipole. Okay, so what is the circular current loop as a magnetic dipole? Elementary magnetic element we can take. Okay, so that is the current loop. So that means you are taking one loop. Suppose if this is the current carrying conductor, you are constructing a small element from it, like this ring I taught you on that day, right? Like this ring. So if you take a small portion from this particular conductor, it forms a circular ring. Okay, it is a small element, and we shall show that the magnetic field due to current in a circular current loop is very similar in behavior than the electric field of an electric dipole. Both are same. Okay. In section 4.5, we've already evaluated the magnetic field on the axis of a circular loop. We already saw. So this is the formula. We got it. Okay, so I hope you remember this formula. Students, always keep this formula in your mind. Again and again, I'm repeatedly saying, students, it's not an easy job to keep everything in your mind. Use your own mnemonics. Right now, there are so many G searches available for you. You can search some help from that. So use your own mnemonics to keep everything in your mind. I'll definitely ask each and every student to write all the formula and its derivation, derive the derivation, derive its unit, and also its suppose if it is possible, you can write its dimensional formula also. Okay, then, and its direction is along the axis and given by the right hand thumb rule. Okay, everything we saw, right? So x is the distance, and x is very much greater than r. From the center, you know that, right? So we saw very small element you have taken, and from the center there is x distance. Here the point P you are considering. Okay, and this is capital R. Okay, everything you know. X is very greater than R. This X is okay, and if X is very greater than R, you can neglect R now. If you neglect R, then it will be x square the whole power 3 by 2. 2 gets cancelled, so x power 3 will be here. Then note that the area of the loop A is equal to pi r square, right? If you consider the total area of a loop is A is equal to pi r square. Okay. Then what it will be if you substitute area is equal to pi r square. So here you have to substitute and then only r square is available. Okay. So you can multiply and divide pi. Multiply and divide pi so that you will be getting pi r square. Instead of pi r square, you can replace A. So that you know, we know I into A is the magnetic dipole moment. Students, I'm always repeating this to you. You can represent P suffix M, then it won't be confusing to you. P suffix M is the magnetic moment due to a magnetic moment, we can say. So that one is electric moment, dipole moment. P suffix E is, okay. Q into 2A, that is electric dipole moment. This is I into A, you can replace by M. Then you'll be getting mu naught M by 2 pi x cube. Okay, if you multiply and divide again 2, it will be mu naught 2m by 4 pi x cube. And you know that mu naught by 4 pi, it is an expression, right? Same like we can able to get, okay? For the electric field, you can just put an analogy with both the electric field and the magnetic field. So you'll be getting mu naught is equal to 1 by epsilon naught. So keep this, okay? And there is a similarity. Yes, that's what I told you, no? So you have to take an analogy between both electric and magnetic field, okay? So all are vectors, keep in your mind. And this is the electric field due to an electric dipole, right? On its axis, you know. 2 into electric dipole moment P is axis, along the axis. So along the equatorial point, you can able to understand. So this one, only P by 4 pi epsilon naught, x cube, okay. But what is this particular result of B for a point in the plane of the loop at a distance x from the center? For a point from the plane of the loop only we are taking, okay, from this, like from point from the plane of a loop, okay, this one, okay, that is this field mu naught M by 4 pi x cube, where x is very much greater than r, okay. So these two you can keep it in your mind, and this can become this this equation is the magnetic dipole. We can able to say it is a point magnetic dipole. Okay. See, for example, a planar current loop is equivalent to a magnetic dipole of dipole moment M is equal to Ia. If you are taking this planar loop, okay, planar loop, and then that loop, you know, from one side the magnetic field is coming out and the other side it is coming down, I mean going down. So coming out and going down, so it forms a dipole. So it is known as point magnetic dipole. Yesterday I taught you in that lesson. What is that? Cross mark and dot mark, you know all these stuffs. Okay, so we already saw so many things. You can go through it again and again. Here also I'm repeating the same. What is going on? It is the magnetic dipole moment. Okay, so which is the analog of electric dipole moment. Again and again the same point is given, and electric monopoles doesn't exist, you know, right? So that we saw, right? If the center of the positive charge and the center of the negative charge coincides, then we won't say that is a monopole. That is a point charge. That is an atom. Okay, wow. Next. In magnetism, a magnetic dipole is the most elementary element. That is the elementary small element, we can say. Suppose if you consider this wire, the magnetic field is around it as a concentric circles we saw. If you consider a small portion of this particular wire, like this ring, okay, then that is the small elementary element like this, okay, like small elementary element. In magnetism, this is called as the dipole. Okay, this one is called as dipole. So if you consider the equivalent of electric charges, magnetic monopoles are not known to exist. Okay, so this is what you have to understand. So plus and minus. So the field outside and field inside. Okay, so it produces a current loop, we know. And first one, magnetic field, and behaves like a magnetic dipole at larger distances, and it is subject to torque like a magnetic needle. This led Ampere to suggest that all magnetism is due to circulating currents. Without current, there is no magnetic field. So this seems to be partly true, and no magnetic monopoles have been seen so far. However, elementary particles such as an electron or a proton also carry an intrinsic magnetic moment, not accounted by circulating currents. That means what they are trying to say, electron, if you consider an electron or a proton, okay, it carry an intrinsic property of magnetic moment, okay, not accounted by the circulating currents. Okay, so if you consider an elementary particle, then it is accounted like that. Okay, it has its own magnetic moment. Okay, you know, electrons are spinning and then it is moving. I taught you already, due to the spin of an electron only, the magnetic moment, the magnetic field will be. So it is accounted only for the intrinsic magnetic moment. If you see, it is accounted only for electron or proton. Okay, not accounted by the circulating currents. Okay. So this property is very important. If you consider a single electron or a proton, then it will be an intrinsic property. The magnetic moment is okay. Or if you are considering a circular loop, definitely the current is accountable. Okay, circulating current is accountable. Then the topic is moving coil galvanometer. Okay, so it's a very interesting topic. The same like that, what you saw, the torque is created. Okay, torque is exerted in the coil. The same here, what is happening within the particular with the coil, here some needle is connected, needle is pivoted, okay, at the center of the coil, so that due to the deflection, the torque is exerted on a coil, right, due to the current flowing through the coil and placed in a magnetic field, okay, uniform magnetic field. The current is circulating through the coil and torque is exerted on it. Due to the torque, that angular deflection, it shows how much current flows on it. So that's what given in the that. So where the pointer is attached, no, that shows the deflection. Okay. Then this is the setup you can able to say. So here the pivot, based on this pivot, this may be able to move. I mean, rotate like this. Okay. So is it clear for you? This is the coil. Okay. And it's a soft iron core given in it. Okay. Yeah, cylindrical soft iron core. It's a cylindrical soft iron core, but a section of the cylindrical soft iron core is given to you. Okay, which not only makes the field radial, but also increases the strength of the magnetic field. That is very important. So that we are choosing this iron core. Iron is increasing the strength of the magnetic field. Then when current flows through the coil, a torque acts on it, that I told you right now. If there are n number of turns in it, then you know how the torque will be n into I into AB. And here a spring is attached to it. See, SP is the spring. It provides a counter torque. That means if the twisting force is there, then again the spring balance it. Okay, the spring creates a restoring force. Okay, if there is a torque, okay, it exerts and then the coil is turned. Then what happens? the spring makes the coil to regain its original path. That means original position. So that we call that as restoring force. Okay. So what is the restoring force here? K into phi, spring force. Okay. So we can take this K phi as the spring force, we can say, or spring torque. Okay. And the spring force is K into X, that will be. But if it is a spring torque, right? So the X will be an angle. X is the linear displacement, right? So what is the torque? Torque is equal to spring force. Suppose if you are taking spring force, what is spring force? Force and torque are same only. So K into X, that is the spring force. So spring torque is, this X becomes some angle. That's it. Okay. So if you substitute, these two gets balanced, then only the equilibrium is maintained here. And in a moving coil galvanometer always it is used for detecting any current in it. Okay. Then it will balance the condition. So everything, pointed out by the, one second, needle deflection. Okay. Okay. Yes. Okay. So once again, yes, Sri Raksha. Once again, I'll text you. Yeah. Okay. I'll catch you up in 5 minutes. Then we'll see now what is phi. So it is an equilibrium condition. Okay, spring force is the restoring force. Okay, so K phi is equal to NIAB by K. Okay, the quantity in brackets, everything is constant except this I. This I is varying. The galvanometer can be used in a number of ways. It can be used as a detector to check if a current is flowing. That's what I told you, right? Check whether if a current is flowing. Then we have come across the usage of the Wheatstone. Already we saw all the bridge balance condition and everything. You can go through it. And the galvanometer is a very sensitive device. For one, suppose we can say, for a small angle of deflection, it shows this full scale is deflected. If the torque is, I mean, if the coil is moving like this, twisted very small angle, then it shows the full, because there is a mirror kept on it, and then here the graduated scale is. Okay. If the coil is slightly twisted, so like this, if the coil is slightly twisted by an angle theta, very small angle theta, then this deflection shows fully. So like this, it is very sensitive, highly sensitive. Okay. So that's what it says. It gives a full scale deflection for a current of the order of microampere. They said in current. Okay. Due to this microampere current, it goes full deflection. So for measuring currents, what we had to do? We had to do some, in order to reduce the sensitivity, we can connect some shunt resistance. Okay, so what is the shunt resistance? Shunt resistance is the low resistance or a small resistance, okay, across the, this is the shunt resistance. It should be connected parallel to the galvanometer. Okay, so it is the process where we can reduce the sensitivity of a galvanometer in order to measure the current. If you want to measure the current along the, across the galvanometer, then what you have to do, you should connect the shunt resistance parallel to the galvanometer. Okay, this is one of the construction part. Okay.